So hello there, my name's Dr. Thomas Blythe. I'm Technical Director at Alchemie Technology. So we, out of our technology centre in Cambridge, United Kingdom, design, develop and build digital, sustainable manufacturing equipment in the aim of revolutionising the textile industry. So all of you here today are aware of the impact that the textile industry is having on our planet today. It is one of the most polluting industries that there is, and as you will see, if you consider the 7 stages of life cycle of apparel from fibre production right the way through to end of life, you see that the biggest contributor by far is textile dyeing and finishing, which accounts for over a third, 36% of all greenhouse gas emissions. That perhaps is unsurprising, given that textile dyeing alone accounts for over 3% of global CO2 emissions, and it is the second largest cause of global water pollution. Unfortunately, that's only going to get worse in the coming years. The demand for fast fashion and the move towards more synthetic fabrics means that the demand for dyed textiles is increasing. A report by Textile Exchange predicts that by 2050, the demand for dyed textiles will exceed 300 million tonnes. That's an increase in threefold from where we stand today. And so using the existing dyeing and finishing technology means that we would be in a position whereby the textile industry was responsible for 2.5 gigatonnes of CO2 emissions by 2050. But the problem goes beyond energy and beyond greenhouse gas emissions. It also includes water. So we've all seen photographs, such as the one shown on screen here, on internet websites, on social media, on printed media. And the impact that the dyeing industry in particular is having on the waterways is critical. Many of these waterways are crucial for life, whether it's for drinking water, whether it's for sanitation, or even for agriculture. And with an increase in population and rising temperatures, water scarcity is threatening human and business survival. A report by the World Bank predicted that by 2030, global demand for water will exceed the supply by 40%, and the fashion industry is largely responsible for that, with more than 1.5 million litres of water required annually. This figure is primarily driven by the fact that currently at least 30 tonnes of water are used to dye 1 tonne of fabric. So moving now on to chemistry, obviously textile dyes, functional finishes are chemicals, and a report by the Chinese Textile Industry Association suggests that 25% of global chemical output stems from textiles alone, and that annually over 1 million tonnes of chemicals are used to apply just functional finishes to apparel and home textiles. So the current approach is therefore very energy intensive, very water intensive and very chemistry intensive. And so whilst brands are making commitments, for example Adidas to reduce their footprint from their supply chain by 30% by 2030, something has to change. And so sort of our opinion, and speaking to many of you sort of over the last day or so, we're all in agreement that the solution is the adoption of new technology. And so that's where we come into play. So our solution is in the form of 2 products, Endeavour, waterless smart dyeing, and Navara, digital finishing. So before I talk a bit more about the products that we offer, I'd like to first of all just give you a bit of an introduction into the technology and how it works. So Alchemie were founded in 2013 with the view to developing an inkjet-inspired liquid application system that was compatible with off-the-shelf chemistry. So off-the-shelf dispersed dyes, reactive dyes, and also functional finishes. And so what we've done over the last 7 years is try to blend the robustness of a more traditional spraying system with the digital benefits offered by inkjet technology. So for example, low minimum order quantity, rapid changeover. And our work has culminated in the device shown in the top left of the screen. So this is what we would call the nozzle. The nozzle comprises a stainless steel tube that you can see at the very bottom. The tube is what's responsible for transporting the chemistry, the liquid, from the tank to the tip. And attached to the tube is a piezo plate. So what we do is we excite the piezo contracts. This being the piezo, I forgot a pointer on there, maybe I have, maybe I haven't. Oh, you can't see it, never mind. So the piezo contracts. As the piezo contracts, the piezo needle moves upwards ever so slightly by a micron or so. Upon relaxation of the piezo, the needle tube moves back down. And this up and down movement is taking place over 100,000 times every second. This develops a resonance in the tube, and the tip where the movement is amplified is moving up and down continuously. What this does is every up and down movement delivers a droplet of liquid, whether that be reactive dye, dispersed dye, or functional finish. We have full digital control over this process, so we can regulate the amplitude of that movement, and we can also regulate the rate of it. So we have full digital control from 0 to maximum from a liquid throughput perspective. The droplets themselves are delivered at very high velocity, so upwards of 10 meters per second, and they have a diameter of about 10 microns in diameter. 10 microns is ideal for fabrics. It can penetrate between filaments, between fibers, and it can get into sort of the very center of the fabric. In terms of numbers, each nozzle is arranged as part of an array. So we have actually 720 nozzles per print bar. Each print bar is 1.8 meters in width. And we have 4 print bars per machine. So there are 2,880 of these nozzles per machine, each one individually addressable. So we can control which nozzles are on, which nozzles are off, and we can control the liquid flow rate. That means we can deliver exceptional color consistency and exceptional performance as far as functional finishing is concerned. This is a full non-contact applicator, so the nozzles sit about 20 millimeters, so just over ½ an inch above the fabric surface. Every meter of fabric receives 1.2 billion digitally defined droplets of liquid. So that, as mentioned, is reactive dye, is dispersed dye, is acid dye, or is functional finish. And that's equivalent to over 270 million droplets per second. To assist penetration further, we've got the droplet size, the droplet velocity. We also work with airflow, so we actively draw air through the fabric. We can control the rate of penetration of dye into the fabric as a result of this, which allows us to work with lightweight microfibers, ripstops, but we can also we've also demonstrated our technology with heavier cotton terry towels, for example. So I'll now move on to the first product, Endeavour. So I'll talk about these numbers in a bit more detail shortly, but Endeavour offers a water reduction of up to, and in most cases, sort of greater than 95% wastewater reduction, 85% less energy, and also a 30% reduction in chemistry. Energy, in rough terms, equals CO2, and so our technology is capable of delivering an up to 85% reduction in carbon footprint associated with textile dyeing in this case. So as mentioned, penetration is key to our technology. The combination of droplet velocity, droplet size, and through fabric airflow means that we can deliver exceptional penetration. Shown here is an electron microscopy image showing a dyed polyester fabric. You will see that all of the filaments, whether that be in the weft or the warp, are dyed homogeneously. Furthermore, the control with which we can apply the dye means that the dye is never applied in excess. So part of this work involves understanding for a particular fabric and a particular dye where the saturation point is for the fabric. Once we understand where the saturation point is, we never go beyond that point. We are always working at or below. That therefore means that after fixation there is minimal unfixed dye left on the fabric, and so not only can we reduce the large volumes of, or eliminate the need for large volumes of water, hot water during the dye application, we can also in most cases eliminate the need for post-dyeing washing. Furthermore, would you believe it, this towel shown on the screen was actually dyed single-sided, so we're able to deliver a penetration enough to colour the terry towel with a basis weight of, I think it was 465 grams per square metre. The elimination of hot water from textile dyeing delivers the 85% energy reduction I spoke of previously. Over the last 2 years or so, we've demonstrated for a range of fabrics, both cotton, cellulosics and polyester, that we can meet industry quality requirements. So I'm talking there about colour fastness and colour consistency. We have 2 processes, Endeavour polyester and Endeavour cotton. So starting first with Endeavour polyester, here is a typical configuration. So the dye is applied to the polyester in 2 stages. We first dye the face of the fabric, we then dry to remove the water. We then apply dye to the second side, the back side of the fabric, we then dry for a second time. So the input to the machine is always prepared for dyeing fabric. After dye application and after drying, you have a fabric in which the dye stuff is on the surface of the filament, it's not yet within the filament, and so the second stage is fixation. After fixation, as mentioned, because the dye is not applied in excess, the majority of the dye stuff that was applied to the fabric is now within the filament, and so as a result, all we need to do is soften the fabric. So we pass the fabric through a low water, low energy softening process whereby we look to remove any auxiliary chemistry that was used in the formulation, so dispersing agents, leveling agents, etc. So after final drying and rewinding, the fabric is then prepared and ready for finishing, if finishing is indeed necessary, depending on the end use of the fabric. In terms of numbers, the elimination of hot water from both the dye application and from the washing means that we're able to deliver significant wastewater reductions and energy reductions versus traditional exhaust dyeing. We're able to deliver a greater than, in most cases, 95% wastewater reduction and an up to 85% energy reduction. And shown in the background are a few examples of some of the fabrics we've worked with, from knits right the way through to polyester chiffon fabrics. Here's a video of our machine in Taiwan. So we have a partner in Taiwan called JS Artex. I am with the JS Artex team in booth A8. So if you'd like to join me afterwards, we can talk about this in a bit more detail. But I'll show you now the machine. So the machine you'll see here is just a dye and dry module. So there's no fixation, and I'll talk you through it as you see it. So you've got your prepared for dyeing fabric entering the machine. Apologies for the video quality. The machine itself is running, in this example, at 18 meters per minute, so 18 linear meters per minute. You'll see the glow of the infrared, the orange glow there, and you'll see the dyed polyester. I think there's a microfiber leaving the machine. So dye, as mentioned, is applied in 2 carriages. The upper carriage you can just see there. And this fabric is now dry and ready for fixation. And so we are in the process of getting the full production line ready in Taiwan. And so Ryan, our JS Artex contact, sort of can talk to you about that in a bit more detail if you're interested. As mentioned, we're in booth A8. So moving now to cotton, the cotton configuration is slightly different. So although the liquid application technology is fundamentally the same, what's different is the process. So unlike polyester dyeing, where we dry and then fix, in the case of cotton, we dye and then we immediately fix using steam. So the dye is applied single-sided in the case of cotton. It's then fixed in the presence of steam, washed to remove the auxiliary chemistry, as mentioned earlier, and any hydrolyzed reactive dye that may occur during that process before finally being dried and rewound. In terms of savings, we've demonstrated savings for both when compared to both exhaust and coal-powered batch dyeing. In the case of the comparison with exhaust dyeing, we've demonstrated that our Endeavour cotton process, that's also compatible with other cellulosics such as rayon and viscose, can deliver an up to, and in most cases greater than, 95% reduction in wastewater, and importantly an up to 70% reduction in energy. In terms of coal-powered batch dyeing, we've demonstrated reductions of up to 85% in wastewater and 40% lower energy. And so sort of between the Endeavour cotton and Endeavour polyester products, we've covered a large percentage of the textile market. So that was Endeavour. As mentioned, 85% lower energy, sort of potentially could deliver an 85% reduction in carbon footprint. Moving now on to Navara, which is our digital finishing technology. So this promises savings of up to 95% less wastewater, 85% less energy, and 50% less chemistry. And I now begin to understand why. So if you consider finishings typically applied during a process called padding, so in padding, the fabric is immersed in a bath temporarily. You then use rollers, nip rollers, to remove the excess. There is a pickup associated with the fabric, and that pickup varies from fabric to fabric and also from sort of composition to composition. In the case of polyester, it might not be possible to pick up less than 50%. In the case of cotton, that figure might be 70%. So every 100 kilograms of fabric that enters the padder will pick up 50 or 70 kilograms of formulation. What that means is that you're having to dilute quite significantly the chemistry. So the chemistry is not applied neat, it's applied with a lot of water. That water requires a lot of energy. That energy is responsible for the carbon footprint of textile finishing. Also, since this is an immersion-based process, since padding that is an immersion-based process, the functional finish is applied across the entire depth of the fabric. However, if you are working with, for example, outdoor wear, where the important aspect is that you've got a water-repellent surface, the question I'd have to ask is, why do you need the water repellent across the entire depth of the fabric? Surely single-sided would be fine. And so that's exactly what we use our technology for. We use our Navara technology to apply the chemistry single-sided. Single-sided application brings with it many benefits. One of these is a potential 50% reduction in chemistry. Additionally, the reduction in chemistry brings with it a reduction in cost. We can also, because we're not working to the same limitation from a pickup perspective, we can also apply the chemistry, in some cases, neat, without the additional water. So in the example I gave previously, if you've got 50 kilograms of formulation per 100 kilograms of fabric. 49 kilograms of that may be water. We can take all of that out of your process. So what that means is that we can significantly reduce the drying energy and as a result the carbon footprint. Single-sided functional finish application also brings with it potential for new product innovation. So you could, if you wanted to, work with 2 Navara applicators applying the same functional finish to both sides of the fabric, and that may be something that you would like to do. The other alternative, of course, is to combine different finishes on different sides of the fabric. So you could, for example, apply a water repellent finish on the outside of the fabric, yet have a wicking or anti-odor on the inside. And our ability to do that is based on the control we have over penetration. So we can regulate the depth at which the DWR and the wicking chemistry propagates through the depth of the fabric. So this is always quite a simple process configuration, but you'll see here that the configuration is very similar to what you would expect to see for padding. The only difference here is we're working with our digital liquid applicators to apply the functional finish rather than working with a padding system. So you will still need to dry and cure the fabric as per a current padding process. So the exact savings that we can deliver for Navara are chemistry dependent. Some chemistries, can be applied without dilution. Some we have to dilute ever so slightly, but in all cases we're able to offer an improvement versus padding. So by means of an example, or examples, in 2020 I think it was, we announced a partnership with HiQ, and over the last 2 or 3 years or so we've been evaluating their chemistry. So we've demonstrated for 2 water repellents, HiQ Eco Dry, which is fluorocarbon free, and HiQ Barrier HMC6, which is a fluorocarbon based chemistry, that we can deliver significant water and energy reductions. In the case of HiQ Eco Dry, we're able to reduce the wet add-on from 65% down to just 28%. Now this 57% reduction in water brings with it a 51% reduction in energy. Similar savings can be seen for HiQ Barrier HMC6, whereby we're able to reduce the padding wet add-on from 65% down to just 31%. This 52% reduction in water brings with it a 46% energy reduction. Perhaps, however, our most impressive results to date have been with HiQ Life, which is a peppermint-based odor control chemistry. In this particular example, we were able to reduce the wet add-on from 80% down to just 80%, or just a little over 80%. This 92% reduction in water brought with it an 84% reduction in energy, and all of the performance was equivalent to what you would expect to deliver with a padding system. So those are our 2 technologies, Endeavour and Navara. Collectively, they could deliver a potential 85% saving in carbon footprint associated with textile dyeing and finishing. So our low energy, low water and low chemistry technology has the potential to enable brands to meet their sustainability goals. So if Adidas are to meet their 30% greenhouse gas reduction by 2030, we believe that they need to adopt new technology. We can also work with brands to develop powerful sustainability credentials that resonate with today's environmentally conscious consumers. Not only that, there's also a digital aspect to our technology, economic short runs, supply chain agility, less inventory, the list goes on. And finally, an important one is that our technology, as you saw from the video earlier, is a much cleaner technology, and therefore it offers an improved working environment for many of the thousands that work in the textile supply chain. So before I conclude, I'd just like to finish with our goal. So our goal is to stop the fashion industry producing over 500 million tonnes of CO2 by 2030. So together we believe that we can transform the textile industry using our clean tech digital manufacturing equipment. So thank you all for your attention, and I'm happy to now invite any questions that anybody may have. Thank you.
First of all, can I ask you to show your appreciation for Thomas, please? Now, whilst you think of questions, I have a couple here. Is the Endeavour commercially available, and how could we arrange to see a real-life demo?
Yes.
Does that mean that we can go out to the Far East and see it?
Yes. Yeah. So Ryan, as mentioned in booth A8, will be able to talk a bit more about the site we have in Taiwan. So we're in the process in Taiwan of getting a full production line set up there. So we expect within the next 2 months to be able to produce dyed fabric. They are commercially available, so we do also have demonstration systems in our Cambridge site in the UK, and I'm happy to talk to anybody who's got any further questions on that, maybe after the discussion.
Are there any questions from the audience here? Now's your opportunity. If not, you need to track him as he wanders back to booth.
Yeah.
So can I ask you once again to show your thanks for Thomas?